I start my presentation by stating that interactive decentralized applications challenge traditional ways of establishing order. And to elaborate on this, let me start first by explaining what I mean by interactive decentralized applications. Well, these are basically the modern applications we use every day. Social apps like instant messengers, multiplayer games, collaborative workflows like Google Docs and Figma and Trello, but also real-time enterprise, cross-organizational workflows, collaborative condition monitoring, etc., etc. What characterizes these applications is that they are interactive, data-driven, so their control of the execution is not, the execution is not controlled, the order of execution is not controlled by the program, if you want, but by the external world, by the arrival of events and new data. These applications nowadays run on massively distributed computing infrastructures, which in addition to, it consists of millions of devices on the edge connected via devices in the fog layer to clouds in the back end. And you just heard the talk by Camilla. We are kind of seeing a trend, a quest for decentralization, moving computations down to the edge and the fog. And there are several reasons why we aim for decentralization. Some of those reasons being, for example, support for offline availability, a better usage of communication resources, low latency, but also what probably Camilla was focusing on, user-controlled data privacy. You see on the left corner down there is kind of the architecture of the decentralized contact tracing app. So people are talking about this idea of local first software running on the edge. Now, why do I state that these kind of new applications or modern applications challenge traditional ways of establishing order? Let's start by looking at what those traditional ways are. Well, computing used to be very simple. In the early days, our models of computing were very simple. The Turing machines, which are our basic model, are simple and ordered. There is basically a list of instructions, an array of states. But as I mentioned, now with the interactive data-driven applications, there is a mismatch of the order of instructions in the program with the order in which data flows and event flows come in. And there is, if you want, no predefined or static order in which the instructions are executed. So our traditional current way to kind of reconcile these mismatching orders between instructions in the program and data flows have been callbacks, which have been accused for causing what is called the callback hell, meaning causing a lot of accidental complexity in the application design, basically because application developers are made responsible for managing the life cycle of callbacks and also for keeping the consistency of the application state across callback calls. To make this a little bit more concrete, more tangible, let's look at this very simple piece of code. If we just look at the code, we see there are some variables defined here, like hour, day, and week, and there is some events that are declared. So we are assuming this is kind of a version of Scala that has first-class support for events like in C#. So we declare here an event tick, new day, new week, whereby tick is a simple event, is triggered from the outside world. New day and new week are composed events, composed by every time a tick occurs and some condition holds. The same thing for new week. And then we have some callbacks here attached to those events. Now what happens? Let's assume tick occurs. This will cause the callback associated to tick to execute, which modifies the state of the variable hour, which occurs here in some predicates, which might turn to true on this change, causing new day to occur. And then as a result, we will execute the callback associated with new day, which changes the variable day. And this in turn might cause new events and so on and so forth. And you see that there is a lot of kind of say spaghetti errors going around in this very simple piece of code. And as I mentioned, I'm assuming that there is some minimal support for events and event composition in the language. If this was not there, the picture will be even more complex. So basically, we have several callbacks cooperating with each other via globally scoped variables. This makes keeping the consistency of the application state difficult. Now, as I mentioned already, our original model of computation was very simple also in terms of state. State was just an array used in a deterministic, non-concurrent way. But then at some point, we moved away from this simple model because we wanted to support, for example, fault tolerance. So we replicated computations in what is called here the infinitely big. And this caused basically losing simplicity and losing universality, because computations that were possible before cannot be are not possible anymore without distributed consensus. The picture is, I mean, the problem is basically the same when we go to infinitely small. That means multi-cores and concurrency for speeding up computations. Now, state is not ordered anymore, and basically our traditional ways to order state were strong consistency guarantees, which were provided by coordination protocols. And there are several of them. I'm just taking here, let's say, the database transactions to illustrate how these coordination protocols establish order. They all have some theory behind them. In case of transactions, this is serializability. And then based on this theory, the engineering kind of creates a transparent illusion of order, meaning application correctness is ensured by design, which is great. But then these were kind of challenged because strong consistency might be expensive. All of us know about the CAP theorem. And then things happened like the NoSQL era, where people gave up on consistency and replaced it with maxims for coping with the CAP problem, like commutative and inverse methods, compensations, which made it easy to scale the infrastructure, but tricky to ensure application correctness, which was kind of okay as long as the same highly skilled engineering teams at Google or Amazon implemented the infrastructure and the applications at the same time. But now, given our decentralized setting, we want to kind of democratize the development of the applications or computations running on the edge too. So we cannot really afford this use of application correctness. The next step in the traditional world was, or a big step towards kind of making systematic decisions about the levels of consistency while keeping availability, is the replicated data types. It has been a very active area of research. The idea of these data types is basically that their state domain is a joint semi-lattice, which makes it easy to merge diverging states without synchronization, with well-defined consistency guarantees, namely a strong eventual consistency. And then in the recent time, we are seeing other research work coming up, which kind of promotes the idea of taking any data type and automatically turning it into a mergeable data type, or supporting replicated data types with mixed consistency, where kind of you have eventual consistency as long as it's okay, and stronger consistency only as much as it is needed to ensure application or the correctness, safety properties of the data type. So far, so good, but these were basically solutions for this, let's say, infinitely big, right? But the infinitely big, the traditional one, is basically only one layer in the new world. This is the layer of clouds and data centers, while in our new world, which is global, dynamic, and open, this layer is under the control of engineering teams at cloud and data center providers and platform providers, but not so the computations that would run on the edge. And kind of distribution in this case is not anymore a technical means to ensure availability and scalability. It's kind of an inherent feature of the world. People and devices and data sources are inherently distributed. The same thing with concurrency is not anymore a matter of speeding up computations, but it's due to people and devices acting and reacting autonomously in time and space. Now, managing state consistency in such an uncontrolled world is conceived to be very challenging. So basically what we have today is decentralized being a wish, but not really a reality. Our interactive applications that run on our devices are basically on what runs on our devices is basically simplified is GUIs to computations that actually occur in the cloud, in data centers. So not much of decentralization. And now the solutions to establish order are there from the old times where, as I said, data was in the clouds and devices on the edge were very simple mobile phones, not our powerful smartphones and other powerful devices we have today. As I mentioned in the last couple of minutes, infrastructure has expanded and improved to enable kind of combinations of availability and consistency, but still the paradigm as itself is kind of logically centralized management is not appropriate for our decentralized goal, decentralization goal. And especially also because we have interactivity. So it's not enough that certain data in the data center, replicated data in the data center becomes automatically synchronized or the synchronization is managed. Also data that depends on that data, computed data that maybe is not in the data center, but on our devices, up to GUI views that user interface views that show the state of the data and allow us to manipulate the data need to be brought to a consistent state kind of instantly, end to end. And this is not ensured by our traditional way to establish order in, let's say, geo-replicated data centers, which are more like kind of have this batch processing or stationary state of the world is the underlying assumption. Okay, to summarize, I hope that I have made the point that there is a quest for new illusions of simplicity. I mean, the world is complex and disorder is the norm, broken state is the norm. And with the new computing infrastructure and the new interactive applications, the problems have become even worse. And if we value decentralization, we cannot rely on skilled teams at cloud companies to ensure application correctness for us. We need to bring the illusions of simplicity that we have developed for this logically centralized setting down to the edge. And my take on this is that, or I argue that programming language-based transparent illusions that leverage the advantages that we have developed in the past for establishing transparency in the centralized setting are the way to go. And in the rest of my talk, I will talk about one particular such language. REScala is an extension of Scala. It's a library-based extension of Scala, if you want. There's a bunch, I mean, the implementation is a bunch of libraries, not really a new language, for interactive decentralized applications that we have been developing with my team in the last maybe 10 years. Well, not quite yet, 8. Let me start by explaining the very basics of REScala, the so-called reactive abstractions. The key abstractions of REScala are events and signals. We all know what events are. Signals may need a little bit of explanation. They are so-called time-changing values. I like this to use the explanation by Sriram Krishnamurthy, where he talks about signals or these reactive abstractions as a third call semantics. We have call by value, eager evaluation, we have call by need, lazy evaluation. Now we have call by reaction, reactive evaluation. So these values that bring, they are kind of self-adjusting. They bring their state automatically up to date anytime values, they depend on computations, they depend on change. A good analogy, I think, is Excel. Anytime you change a cell in an Excel sheet, anything else that depends on the value of this cell is brought automatically up to date. The reactions are managed. It's not that you need to manage them explicitly. And basically, this is, I mean, the key idea behind reactive languages and REScala, that reactions are managed. And these signals can be arbitrarily composed into more complex or derived ones, as we call them. And we have predefined combinators for composing them. And they are, both events and signals are kind of subtypes, if you want, of a higher type reactives. They are kind of can be transformed to each other, can be conversed to each other, they can be composed into expressions. Basically, the key take-home message here is that changes are automatically and consistently propagated to dependent computations, to chains of computations. To show you how this looks like a little bit in code, consider this piece of code on the right. You don't need to read it. I will kind of take you through the important things in this piece of code. Basically, you see that we define some values, remove all, create to-do, create task list, and eventually call at the end the UI display method with task list as a parameter. Now, values can be used to define other values. This is depicted here by the white arrows, like remove all is used in the definition of task list, or create to do in the definition of create tasks, and so on and so forth. And these white arrows depict also change paths. So whenever remove all changes, task list is brought up to date automatically. And the same thing here, whenever task list changes, the display is refreshed, and there is no callbacks here. So the execution is kind of sequential. And what makes this possible is basically, as I mentioned, the managed reaction. The runtime takes care of managing dependencies, data dependencies, and propagating changes. And the idea is that the user-defined computations, they are encapsulated into nodes in a dependency graph. Any change from the outside world does not change the user-defined computations directly, but any change goes through the propagation algorithm, which then reevaluates all nodes from some input nodes to the top of the graph, or any node that needs to be, that is in the path, in the change path, is reevaluated. And when we have reevaluations, they kind of invoke user-defined computations. The propagation of changes, the reevaluations happen in the topological order of the nodes in the graph. And this is what ensures what we call synchronous semantics. So all changes related to, all reevaluations that are caused or depend on one change happen, if you want, at once. So the dependency graph moves on any change from one consistent resting state to the next consistent resting state. There is no intermediate state that is observable from the outside. And this becomes easier to illustrate when we look at this change, this flow through the graph, which affects the node in the middle via two paths. And even if there are two paths along which we can change this node, we don't see two values of the node, two results of the reevaluation of the nodes, but only one. So there is this only once reevaluation semantics, all due to the topological order, or all input nodes have to evaluate first before this node in the middle can reevaluate. And this kind of simplifies reasoning about computations written in such a reactive style. And we have done some studies, empirical studies, that indeed show that there is a positive effect of reactive abstractions on the comprehension of software. And the more important message is that this kind of managed reaction makes it not only easier for the developers to reason about the software, it makes it also easier, or empowers the language runtime to establish automatically order, for example, in the presence of concurrent flows. What's the problem? Well, even two flows that are synchronous, consistent, when they execute concurrently, we may see glitches. And to solve, here the orange and the green flows, they kind of affect the dependency, a shared node in the dependency graph, and this can cause this kind of a race problem. We make kind of, to solve this problem, we view these reactive flows as if they were transactions in the sense of database transactions. And this kind of synchronous semantics of them actually has this flavor of all changes related to an input change happen at once logically. And we bring this also to the concurrent world. So even if orange and green happen actually concurrently, from the outside, it occurs as if they happen sequentially one after the other, moving the state of the application from one resting state to another consistent resting state. And the good thing is that for these kind of reactive transactions, we have proven that we ensure abort-free strict serializability, which is a very strong property, actually, especially this abort-free. And to ensure this, we make use of the reactive programming features. I will come to this point very soon. And as a result of this semantics, abort-free strict serializability, and the way we integrate transactions into the system, we ensure syntactically and semantically transparent illusions, in the sense that you can take an existing REScala program, which was not written for a multi-threaded setting, and execute it in a multi-threaded setting, and without changing any thing in the program itself. And the behavior, there is no change in behavior that is observable, because the execution happens with abort-free strict serializability semantics. To give you just a glimpse of how we ensure this, we basically make use of ideas from multi-version concurrency control. So there isn't one value associated with each node in the dependency graph, but several versions. So each node can have several versions at the same time, one per concurrently executing reactive transaction. And when the transaction starts, a new one, the orange, it basically puts empty versions in all nodes that it might affect. We know exactly which nodes this new transaction could eventually affect, because we can just compute the transitive closure starting with the input node that has changed to the root of the graph. And if it happens that some other transaction or update transaction starts concurrently, we do the same thing. And once we get to a node which is affected by both transactions, we establish an order once and forever, if you want, orange before green in that case. And even if they occur or arrive at the node M in different order, we kind of make sure that the order is established. Once they have put their versions on place, their execution plan, if you want, they can start executing. And then this order of the versions is used to ensure at the same time glitch freedom as well as serializability. So if, let's assume, orange reaches the wants to reevaluate N, it will realize that it cannot do so because one of the predecessors has still an empty orange version. Green can also not reevaluate N because green is ordered behind orange and orange has still an empty version. So the only way to progress is that orange reevaluates node K, fills there the version, and at this point it can continue with the reevaluation of N, which in that case, let's assume the graph can change dynamically. So we reevaluate N, or orange reevaluates N, and at this point, due to some dynamic conditions, let's say a new dependency occurs. So the dependency between I and N disappears, but then there is a new dependency between the node J and N that is established. And let's assume that now concurrently another transaction, pink in this case, start. But the good thing is that orange is under the control, knows exactly the state of the dependency graph. So it can rewrite things so that everything occurs as if we knew from the very beginning that the pink transaction also executes concurrently to the orange and green. What does it mean in this simple example? It means that it puts versions on behalf of the pink transaction in all nodes that are affected by the pink. It can exactly see which nodes those are. It orders pink now behind green. And then at this point, all three can continue their execution, fill their respective versions, and bring the whole system into the new, the next state, consistent state. And all this, I mean, this strong consistency guarantee that we can give out of the box for the application is due to the declarative programming model. And these are the features on the slide that are crucial. The explicit data dependencies allow us basically to determine the evaluation schedule ahead of time, which avoids deadlocks and ports. Then the topological order of the evaluation is key, as I hope I illustrated, in even supporting this deadlock-free, safe, thread-safe propagation in the case where the dynamic graph changes on the fly. And then the write-once semantics makes it possible that any transaction can kind of commit, if you want, the value of a version as soon as it fills the version. Instantly, it's visible to the other transaction because it cannot change anymore. We know that there will be no changes beyond that point, so we can make the value visible. And this allows kind of pipeline concurrent propagations. Even if we have strong consistency, we can execute the transactions a little bit concurrently. And then by the fact that we encapsulate state in reactive abstractions allows us to plug thread safety transparently into the application. So any change from the outside world is automatically by the runtime wrapped into a reactive transaction. And I don't have time, but we support also the same semantics for distributed flows. Of course, this cannot come for completely free. We need some distributed coordination in that case, but only for transaction graph testing. So basically, we have minimized the amount of synchronization that we need, that it's hidden from the application developers anyway. But still, there is some coordination needed, which in the case of interactive decentralized applications might be a no-go or might kind of damage availability. That's why in the language we also have support for fault-tolerant reactive flows. And basically, to ensure this, to ensure fault tolerance, and when I say fault tolerance, I mean stop crash failures or partitions, both of them. And to this end, to ensure fault tolerance, we kind of make use and repurpose. I will come to say what I mean by repurposing. Conflict-free replicated data types. So to give you an idea, let's look again at the piece of code that I showed before. Now you see some new things here, like replicated list or last writers wins. These are conflict-free replicated data types, which we kind of encapsulate into reactives. You see they are encapsulated into signal abstractions or events. That means they also have this reactive behavior. And once we do so, now we can collaboratively change the to-do list or work on the to-do list on two different devices. Two different persons can share the same to-do list, and changes are made automatically consistent as soon as there is connectivity. I said we repurpose a bit the replicated data types because we don't use them here for the purpose of replication for increasing efficiency, but rather as for modeling communication between peers as a data type, if you want. So what we have done is that we have added support to the language for replicated data types. When I say added support means we want to enable normal application developers, not data storage providers, to define custom replicated data types with ease. So there are language constructs that makes this easier. The runtime ensures composability automatically. CRDTS are great, but hard to compose, or not so easy to compose, let's put it this way. And we have also runtime support for verifying that their merge operators indeed fulfill the mathematical properties that they have to support. Another thing that we have is that we transparently can encrypt these replicated data types, because in a setting where everything is decentralized peer-to-peer, there might be peers that are not trustworthy, or in order to enable connectivity, even if there is no direct connectivity between two peers, we might want to use intermediaries which are not trusted. That's why we have added a layer of transparent encryption, but also model this kind of, this is itself again a replicated data type. And then behind the scenes, the replicated data types kind of encapsulate synchronization algorithms for various network topologies. It can be client server, peer-to-peer, or even delay tolerant networks. Now, back to the big picture of the application, what we get now is basically conflict-free distributed flows. What do I mean? Instead of having this one dependency graph, let's say we have 3 nodes, we have replicated the state, which are those nodes in the middle. At every point in the graph where we need to connect to the other nodes via, let's say, unreliable network connections. Now, the distributed reactives, conflict-free distributed reactives, have the same behavior as other reactives, which means locally they behave as any reactive. They propagate changes to their nodes that depend on them. But in addition, they also broadcast change their state whenever possible to the peers. And once such a broadcast come, they also propagate it locally through the dependency graph, which ensures this end-to-end strong eventual consistency. What I mean by end-to-end is from an input, from the state of some input node to the state of some data types that are in the cloud, to some state that is computed from the storage and displayed on some graphical user interfaces. So in general, this picture shows that the state of a REScala application basically is maybe distributed across devices and data centers. There might be some parts of the applications that are connected, for example, to the data center via reliable connections, and others that have unreliable connections. On those parts where we have unreliable connections, the states might diverge at some point, but eventually they are synchronized again. And I didn't mention this so far, but we also have support for crash recovery, so devices may crash, but we periodically save the state, and then once the device is up and running again, we recover the state and propagate it to the other node. So the key thing is that also for this crash recovery, we use the reactive programming feature to fit recovery into the normal change propagation. And the question is, how do we go from individual CRDTs with this strong eventual consistency property to an application level strong eventual consistency? This is very easy. This happens automatically. In general, once you compose two CRDTs, you have to make sure that, if some change, if there is some transaction that changes two CRDTs, you need to make sure that these changes happen in a causal manner. And this often requires that you embed CRDTs into each other. You have to define new CRDTs for the composition, which is non-modular. In our case, we don't need to do anything because the reactive transactions I mentioned bring the state of the entire application from one consistent state to the next bigger consistent state. So the entire state of the application itself is a CRDT, if you want. Okay, to summarize, I think, I need to summarize, but I am also almost at the end. Since we have support for both this strong, consistent flows, which minimal coordination, but which are fault intolerant, and on the other hand, support for synchronization-free and fault-tolerant flows with strong eventual consistency, actually causal consistency. Within the same system, the runtime supports both in a modular way. We can mix and match if we want, so that, as I mentioned, parts of the application can run under strong consistency guarantees and parts of the application under strong eventual consistency guarantees, but it's the responsibility, so to say, of the application developer to configure the runtime such that to ensure that there is this hybrid consistency model. And I mentioned in the very beginning, given that we want to democratize the development of such applications, it's desirable to take this responsibility away from the developer. And that's why we are currently working on this kind of work on progress on automatically deriving the consistency levels that are needed to ensure application level safety properties. Compared to the state I presented so far, we have the input program, but in addition to it, we have some behavioral specifications, especially invariant safety, invariance, application level safety invariance. They don't talk about consistency levels. They talk about application semantics, like that the value of some reactive must be non-negative during the whole execution of the application. And then we have extended the language runtime to with some verification machinery, which takes this invariance and based on the knowledge about the data flow of the application, decides which flows need to run under strong consistency guarantees in order to ensure the application level safety invariant. And then the result is what we call synchronization points. Those are the flows that need to be synchronized, and then we generate, synthesize, if you want, the synchronization logic. Okay, with this, I'd like to summarize. I started by saying that when we look at interactive data-driven applications that run on a globally distributed computing infrastructure and in a decentralized way, kind of we move from an order to a disordered and a completely out of control world. And I mentioned that our traditional ways to reestablish order are not suitable for this setting, and we need to kind of bring the results that we have achieved in a centralized setting down to on the edge, if you want. And I argued that programming language integration is key in doing so, in order to make life simple for application developers, not to put responsibility on their shoulder to ensure, or as less as it gets, to ensure application correctness. We want to get it out of the box. The language should provide it by design. And then I presented one such language project. We have been working, the REScala project, which support reactive abstractions built in. And then I explained how we can make reactive updates serializable in a concurrent distributing setting, and then moved on to explain how we make them fault tolerant, and even how we support hybrid flows, kind of a mixed or hybrid consistency model, have use as much strong consistency as it is needed to ensure application level safety properties. With this, I'd like to thank you, and thank you the REScala team, but also thank you very much for your attention, and be happy to take questions.